History of Haskell. Haskell is a purely functional programming language named after the mathematician Haskell Curry. The development of Haskell began in 1987 when a committee of researchers aimed to create a strong, statically typed, purely functional language. Haskell 1.0 was released in 1990. The inception of Haskell can be traced back to a conference in 1987 where several researchers in functional programming language design met to discuss the creation of a better functional language. They wanted to include features from existing languages while also addressing shortcomings. The result was that Haskell combined ideas from several research languages, such as Miranda and ML, to become a standardized, purely functional language. The language has undergone several iterations, with the major release being Haskell 98, which aimed for stability and wide acceptability. The most recent standard is Haskell 2010, with some extensions that are widely used but not officially standardized. Functional programming concepts. In functional programming, functions are considered pure if they satisfy two main conditions. They always produce the same output for the same input, no side effects, and they do not affect the state outside of the function, no state mutation. Here's a simple example. The square function is pure because it will always produce the same result for the same input value. It does not modify any outside state or variables, and has no side effects like printing to console or reading a file. Benefits of Haskell. Haskell is a purely functional programming language known for its expressiveness, strong static type system, and powerful abstractions. Here's a basic example of a Haskell function. This code defines a function fib that computes the nth Fibonacci number. Haskell's syntax is concise, and the function is defined with pattern matching, which is a feature that allows complex logic to be expressed clearly. Because Haskell is pure, the fib function has no side effects. Every time you call fib with a particular number, you're guaranteed to get the same result. This makes reasoning about your code much easier and helps with maintainability and debugging. Installing GHC and GHCi. GHC, Glasgow Haskell Compiler, is the main compiler for Haskell, and GHCi is its interactive environment. To begin using Haskell, you'll need to install GHC, which automatically comes with GHCi. Installation can differ based on your operating system. For most users, the easiest way to install GHC along with its tools such as GHCi is to install the Haskell platform. The Haskell platform is a comprehensive binary distribution of GHC, libraries, and tools. You can download it from the official Haskell website. Linux users can typically install GHC using their package manager, while Windows and Mac OS users can download the installer directly from the Haskell platform page. After installation, you can verify the installation by running GHC version and GHCi commands in the terminal. Stack and Cabal. Stack and Cabal are both tools for Haskell project management. Cabal is the older tool and it manages Haskell package metadata and builds. Stack, introduced later, is built on top of Cabal but focuses on reproducible builds, managing compiler versions, and ensuring consistent package sets. The command stack new my project creates a new Haskell project named my project with a default stack template. It sets up the necessary files for a Haskell application, including a project configuration file, stack.yaml, a Cabal file, myproject.cabal, and source code files in the app and src directories. Basic GHCi usage. GHCi is the interactive environment for GHC, the Glasgow Haskell compiler. It allows you to write Haskell expressions and get immediate feedback, which makes it an excellent tool for learning and experimenting. Below is how you can use GHCi to load a Haskell file and execute functions. The load command tells GHCi to load a Haskell script file. Replace your Haskell file.hs with the actual file name containing your Haskell code. After loading the file, you can call functions defined within that file directly in the GHCi prompt. SumFunction 1020 is an example of calling a function named SumFunction with arguments 10 and 20. If SumFunction is defined in the loaded file, GHCi will execute the function and display the result. Hello World program. The Hello World program is often the first step in learning a new programming language. It's a simple program that outputs the phrase Hello World on the screen. In Haskell, we'll write this program, showcasing the structure and syntax of a basic Haskell script. In this Haskell program, main is the entry point of the program. It has a type signature, main IO, which indicates that main is an IO input-output action that returns a unit value. Put*ln is a standard output function that takes a string and prints it to the terminal, followed by a new line. The string hello world is the argument given to put*ln. When executed, this program will print hello world to the shell where it is run. Expressions and functions. In Haskell, an expression is a combination of values, functions, operators, and parentheses that the language interprets and computes to produce another value. Every valid piece of code that can be evaluated to yield a value is considered an expression. Let's look at a simple arithmetic expression. This expression involves two integer values, 3 and 2, and two arithmetic operators, plus addition and store multiplication. According to Haskell's operator precedence, the multiplication is performed first, resulting in 4 now 2, which evaluates to 8. Then, the addition is performed, 3 plus 8, which evaluates to the final result, 11. Basic data types, int, bool, char, etc. In Haskell, basic data types include int for integers, bool for Boolean values, and char for characters. Each of these types encompasses a variety of values. Int represents whole numbers, bool can be either true or false, and char encapsulates single Unicode characters. Haskell is statically typed, which means the type of every expression is known at compile time. The code block defines three constants, example int, example bool, and example char, each annotated with their respective Haskell data types. Example int is an integer value assigned to 42, example bool is a Boolean value set to true, and example char is a character holding the value a. Type annotations are not required, but are included here for clarity. Type inference. Type inference in Haskell refers to the compiler's ability to deduce the types of expressions automatically. This means that you do not always have to explicitly state the type of every variable and function, as the compiler can infer this information from the context in which they are used. Let's look at a simple example where we define a function without explicitly stating its type. In the given code, the function SumNumbers takes two parameters, x and y. Since plus is an operator that works with numbers, the compiler infers that x and y must be numbers, int, integer, float, double, etc. It also infers the return type of the function as a number since the result of plus is a number. In the main function, we call SumNumbers with integer arguments 5 and 6, which makes Haskell infer that the specific type for x and y is int. Thus, no explicit type annotations are needed. And the type inference system keeps the code concise and readable. Lists and tuples. In Haskell, a list is a collection of elements of the same type. Lists are denoted by square brackets, with elements separated by commas. They can be manipulated in various ways, such as concatenation, accessing elements, and list comprehensions. The code demonstrates three fundamental operations on lists. The ++ operator concatenates two lists. The head function retrieves the first element of a list. A list comprehension is shown, generating a list of numbers, where each is twice the corresponding element from the list 1, 5. Function declaration and definition. In Haskell, a function is declared by specifying its name, a list of parameters, and the resulting type. The definition follows the declaration, establishing the relationship between the inputs and the output. The preamble add int is a type signature. It declares a function named add that takes two integers, int, and returns an integer, int. The definition add xy equals x plus y defines the function's behavior. It takes two arguments, x and y, and returns their sum. The equals sign separates the function's name and parameters from its body. Pattern matching. Pattern matching in Haskell allows you to check a value against a pattern. It's a more powerful version of a switch case you might find in other languages. It is used extensively in function definitions, where you can match on arguments and in case expressions. If a value satisfies a pattern, Haskell executes the corresponding code block. In the code, the function myHead takes a list and returns its head, first element. The first pattern checks if the list is empty, and if so, it produces an error. The second pattern, xscore, matches a non-empty list, binding the head of the list to x, and ignoring the rest of the list using the underscore for. If myHead is called with a non-empty list, it returns the head element. Guards. In Haskell, guards are a way to test which of several values a given input satisfies before deciding which result to return. They are used as a more readable alternative to complex if-then-else expressions for functions with multiple conditions. In this code, bmitell is a function that takes two real float arguments, weight and height, and returns a string. Guards are introduced by the pipe symbol ls and are followed by a Boolean expression. If the expression evaluates to true, the corresponding right-hand side of the guard is returned. The where keyword introduces a local definition for BMI, which is used in all the guards. If none of the guards evaluate to true, the otherwise guard, which is always true, catches all other cases. Let and where bindings. In Haskell, let bindings allow us to define local variables within an expression. The general syntax is let bindings in expression. The scope of variables defined with let is limited to the in part of the expression. In the code, square+1 is a function that takes a parameter x. A local variable y is defined using a let binding, which holds the square of x. The in part of the expression adds 1 to y and returns the result. Case expressions. In Haskell, the case expression allows you to evaluate an expression and branch the code depending on the value of the evaluation. This is similar to the switch case statement in imperative languages. It's particularly useful for pattern matching against complex data types, allowing for more readable and expressive code. In this code, describeList is a function that takes a list, xs, and returns a string describing the list. It uses a case expression to pattern match against three possible conditions: an empty list, a list with exactly one element, and a list with more than one element. For each case, it returns a corresponding string. The underscore score is used as a wildcard to match any list with more than one element. This example illustrates how case expressions offer clear and concise branches in Haskell code. Basic I/O operations. In Haskell, I/O operations are handled differently from pure functions. The getLine function is used to read a line of input from standard input, usually the keyboard. Here's a simple program that prompts the user for their name and then greets them. The program uses put*ln to print a prompt to the console. It then uses getLine to read user input and binds the result to the name variable using the snads operator. Finally, it uses another put*n to greet the user by name. This code must be within a do block since it involves I/O operations. If-then-else expressions. In Haskell, an if-then-else expression allows for basic conditional logic. The syntax consists of an if keyword followed by a condition, then a then keyword, and an expression to evaluate if the condition is true, and an else keyword with an expression if the condition is false. The condition must be a Boolean expression, and both the then and else branches must result in the same type because Haskell is a statically typed language. The given code defines a function absolute value that takes one parameter x. It uses an if-then-else expression to check whether x is negative. If x is less than 0, the function returns the negated value of x, effectively calculating the absolute value. If x is not negative, it returns x as is. The if-then-else expression ensures that no matter the input, a non-negative value is returned. Recursive functions. In Haskell, recursion is a fundamental concept where a function calls itself to solve a problem. A well-defined recursive function requires a base case to stop recursion and a recursive step to reduce the problem size. Let's take factorial as an example. This code defines a function factorial that calculates the factorial of a non-negative integer. The base case is defined for 0, returning 1. For any other positive integer n, it multiplies n by the factorial of n-1, which is the recursive step. Recursion continues until it reaches the base case, which terminates the recursion. List comprehensions. List comprehensions in Haskell are a concise way to create lists based on existing lists. They are similar to the set comprehension notation in mathematics and can include conditions and multiple sources. They can be considered as syntactic sugar for the map and filter functions. The code is a list comprehension that generates the squares of all odd numbers between 1 and 10. X is drawn from the list 1, 10, and is then filtered by the predicate odd x to include only odd numbers. Each selected x is then squared by x squared before being added to the output list. Higher-order functions: map, filter, fold. In Haskell, higher-order functions allow us to operate on lists or other collections in a concise and expressive manner. These functions take other functions as arguments, enabling powerful patterns of computation. Three fundamental higher-order functions are map, filter, and fold. Map applies a function to every element of a list, filter removes elements that do not satisfy a predicate, and fold, also known as reduce in some languages, aggregates elements in a list into a single value. In the code, map example uses map to double each number in the list from 1 to 5, resulting in 2, 4, 6, 8, 10. Filter example uses filter to keep only the numbers greater than 2 from the list 1 to 5, leading to 3, 4, 5. Fold example uses foldal, which stands for fold left, with the addition operation to sum up the numbers in the list from 1 to 5, which computes to 15. Lambda expressions. In Haskell, lambda expressions are used to create anonymous functions, which are functions without a name. They are particularly useful when you need to pass a function as an argument to a higher-order function, or when you want a concise way to define a function inline. The given code defines a lambda expression that takes two arguments, x and y, and returns their sum. It is written using a backslash, followed by a space-separated list of parameters, an arrow, and then the function body. Lambda expressions in Haskell can be used wherever a function is expected. Function composition and pipelining. In Haskell, function composition is the process of combining two or more functions in such a way that the output of one function becomes the input of the next. It's a concise way to create new functions from existing ones without having to write detailed definitions. The operator for function composition is the dot, and it's read from right to left. The example shows how function composition works. The function f adds 1 to its input, while g converts a character to uppercase. H is a new function that takes a string, converts each character to its ASCII value using ORD, adds 1 to the ASCII value, and then converts it back to a character using toUpper, effectively creating a function that processes a string by mapping each character through this composed post function gf_ord. Operators, infix, and custom definition. In Haskell, an operator is a function that can be applied using infix notation. Most common operators like plus, == are infix by default. You can also define custom infix operators using symbols. To use a regular function infix, enclose it in backticks. To use an infix operator as a prefix function, enclose it in parentheses. This code snippet first shows the use of a custom function myCustomFunc in infix position with backticks. Next, we define the associativity and precedence level of the custom infix function using infixl6 myCustomFunc. The function itself takes two int arguments and returns an int. The custom infix function doubles the first argument and adds it to the second. Type classes. In Haskell, a type class is a sort of interface that defines some behavior. If a type is a member of a type class, it supports and implements the behavior the type class describes. Different types can be instances of the same type class, meaning they support the same set of operations. The above code defines a type class named EQ, which includes types that can be compared for equality and inequality. It has two functions, =6 for checking equality and /equals for checking inequality. Default implementations are provided. If you define =, you get == for free by negating =, and vice versa. An instance of EQ for a particular type provides concrete definitions for these functions. Defining new data types. In Haskell, you can define new data types using the data keyword. This is especially useful for creating types that closely represent concepts within your domain. Let's define a simple data type to represent geometric shapes. The data keyword introduces a new data type declaration. Shape is the name of the new type. It has 3 constructors: circle, rectangle, and square. Each constructor is followed by the type of its parameters. Circle takes 1 float, representing its radius. Rectangle takes 2 floats for its width and height. Square takes a single float for the length of its side. Deriving show allows us to print shapes as strings for easy debugging. Constructors are used to create new values of the type shape. Algebraic data types, ADTs. Algebraic data types are a way to define custom data types in Haskell. They are algebraic because we can combine existing types in new ways, like creating sums and products of types. ADTs comprise of sum types, also known as tagged or discriminated unions, and product types, similar to records or structures in other languages. In the code, shape is an algebraic data type that has 2 constructors, circle and rectangle. Circle takes a single float, representing the radius. Rectangle takes 2 float values, representing the width and height. Each constructor can be thought of as a different option for the type of shape. Here, shape is a sum type because a value of type shape can be either a circle or a rectangle, but not both at the same time. Type synonyms. In Haskell, a type synonym is simply an alternative name for an existing type. Type synonyms are created using the type keyword, and they can be used to make type signatures more readable or to convey the intended use of a type more clearly. In the provided code, string is defined as a synonym for char, which is a list of characters. Similarly, phone number, name, and age are defined as type synonyms for string and int respectively. Person is a tuple type comprising name and age. Note that these synonyms do not create new types. They merely provide alternative names to existing types for clarity. You can use phone number, name, and person in type annotations, and the compiler will treat them as their underlying types. Polymorphic functions. In Haskell, polymorphic functions allow for generality in the types of their arguments. These functions can operate on variables of any type. This is extremely powerful, making functions highly reusable. One common type of polymorphism is parametric polymorphism, where one or more types are not specified by the function, but are instead taken as parameters. In the code provided, myLength is a polymorphic function that calculates the length of a list. The type signature a int means that it takes a list of any type a and returns an int. Folder is a higher order function that takes another function, an initial accumulator value, and a list, then processes the list by applying the function from right to left. The polymorphic nature of myLength, given by the type variable a, allows it to accept a list of any type, whether it's a list of ints, chars, or any other data type. Custom type class definitions. In Haskell, a type class is a sort of interface that defines some behavior. If a type is an instance of a type class, it supports and implements the behavior described by that type class. Let's define a custom type class printable, where types that implement this class must define a function stringify that converts a value to a string. We define a custom type class called printable with a single function, stringify, that all instances of this class must implement. Then we create 2 instances of this type class. The first is for the int type, where stringify prefixes the string integer to the show version of the integer. The second one is for bool, where stringify returns Boolean true or Boolean false, depending on the Boolean value. This allows us to use stringify on any type for which we have defined a printable instance, providing a custom string representation. Instance declarations. In Haskell, an instance declaration is used to create concrete implementations of a type class for specific data types. This allows the data type to be used with any function that requires a type that's an instance of that particular type class. In the provided code, we define a type class EQ with one function, equal, which is used for equality testing. Then we provide an instance declaration of the EQ class for the data type bool. This declaration specifies how equality is determined for Boolean values. True is only equal to true, false is only equal to false, and any other combination results in false. This enables us to use equals on Boolean values throughout our Haskell programs. Parametric polymorphism. In Haskell, parametric polymorphism allows functions to be written without specifying the exact types they will operate on. This is akin to generics in other languages, where type parameters are used to achieve this form of polymorphism. A classic example is the identity function, which returns whatever value is passed to it, regardless of type. The ID function's type signature AA indicates that it takes an argument of some type A and returns a value of the same type. The lowercase a is a type variable representing any type. This is what makes ID parametrically polymorphic. It works with any type. In the body of the function, we simply return the input x, demonstrating that ID performs no operations other than outputting its input unchanged. Type constraints. In Haskell, type constraints restrict the types that can be used in a particular context. These constraints ensure that a function can operate on different types as long as they satisfy certain properties or belong to certain type classes. Type classes can be thought of as interfaces that define a set of functions that types must implement if they are to be considered members of the type class. In the code snippet, f is a function that takes two arguments x and y and returns a bool. The type signature f num a ord a equals a minus bool states that for all types a, as long as a is an instance of the num and ord type classes, this function can operate on x and y. The num constraint ensures that the plus operation is valid for a, and the ord constraint ensures that the join comparison can be applied. In this case, f adds two numbers and checks if the result is greater than 100. Module syntax and organization. In Haskell, a module is a collection of related functions, types, and type classes. Modules are defined using the module keyword, followed by the module name and an export list. The export list specifies which names are to be visible outside the module. The module geometry declares two functions, area and perimeter, intended for external use. The names inside the parentheses are the exported entities. The where keyword begins the module's body. Functions area and perimeter calculate the area and perimeter of a square, given a side length respectively. Importing and exporting modules. In Haskell, modules group related functions, types, and type classes. Importing a module makes its exported members available in another module. The code imports two specific functions, nub and sort, from the data.list module. The remove duplicates and sort function is then defined to first remove duplicates from a list using nub and then sort the result with sort. Only nub and sort are available from data.list in this scope. Building projects with Stack. Stack is a cross-platform program for developing Haskell projects. It is aimed at Haskellers both new and experienced. It is intended to simplify the process of writing real-world Haskell code by automating the administrative tasks, ensuring reproducible builds, and providing a curated set of packages through StackEdge. This sequence of commands is used to create and build a new Haskell project using Stack. Stack new my project initializes a new Stack project with a default configuration. Changing the current directory to the new project folder with cd my project is necessary to act on the project. Stack setup will install the appropriate GHC, Glasgow Haskell compiler, if necessary. Stack build compiles the project, and stack exec myproject.exe runs the compiled executable. Replace myproject.exe with the name of the executable defined in the project stack.yaml or package.yaml file. Understanding Cabal files. A Cabal file is used to describe a Haskell package so it can be built and packaged in a consistent and reproducible way. It includes metadata about the package and a description of its components. This example Cabal file defines a package named myPackage with version 0.1.00. It gives a brief synopsis, specifies the license along with the location of the license file, and includes the author's information. The category is set to development, and it specifies the build type and the minimum Cabal version required. The executable section names the executable my_executable, sets src as the directory to look for source files, specifies main.hs as the main entry file, defines dependencies on the base package and some other package, and designates the default language as Haskell 2010. Exploring hackage and stackage. Hackage is a large collection of Haskell libraries and applications. To use a package from Hackage, you typically use the Cabal build system, which can download and install dependencies for your projects. The example code uses Cabal install to add a package from Hackage to your Haskell project. Replace package name with the actual name of the package you want to install. Using libraries from Hackage. In Haskell, Hackage is the primary package repository where libraries are shared. To use a library from Hackage, you usually need to install it using Cabal or Stack, which are Haskell's build tools. In the code, we import the data text module under a qualified name T. This prevents namespace collisions between the prelude and data.text. We define a function greet that takes a text type as an argument and returns a greeting by appending the string hello to the input name. The data text module is part of the text package, which must be added to your project's dependencies if you want to use it. Creating and distributing a package. To create a Haskell package, one typically uses the Cabal build system, which is part of the Haskell platform. Here we'll define a simple library package. The provided code is a simple Cabal file named mypackage.cabal for a library package. It specifies basic package information like name, version, synopsis, and the package category. It has a BSD3 license and identifies the source directory that contains Haskell source files as srar. The library section declares which modules are exposed by the library, in this case, my module. It also lists the dependencies necessary to compile the library, such as the base package between versions 4.10 and less than 5. The default language specifies which version of Haskell is used. Managing dependencies. In Haskell, managing dependencies involves specifying external libraries your project requires. This is usually done in a file named cabal.project when using Cabal or stack.yaml when using Stack, along with associated .cabal files containing library and executable definitions. The package manager resolves and fetches these dependencies during the build process. The code snippet is an example section from a .cabal file specifying dependencies. The first line indicates that the package depends on the ASIN library, with a version constraint demanding a version greater or equal to 1.4 but less than 1.5. The next two lines state dependencies on the text and bytestring libraries without version constraints, which means the latest compatible versions will be used. The package manager uses this to ensure the necessary libraries are installed and their correct versions are used.